Hello, in this video we're going to be talking about RC circuits, fun and exciting circuits that use resistors and capacitors connected together to charge up and store energy and then to discharge it later for later use. We're going to mostly focus in this video just on how to use the equations, do some exponential decay math, yeah, just get into the mathematical equations, how we do these. Okay. So, main thing to know from some experimenting, observing, is that the discharge of a capacitor is exponential. This is an exponential decay situation. Remember, capacitor is a device, two metal plates separated by some distance with a vacuum or a material in between them, designed to hold charge on one plate and create an electric field between them and store electric energy. Use these in like old cameras and stuff a lot to store up a lot of energy and then release it all at once. But when you release it, it releases like this. It releases like exponential decay. So when I hook this up to a discharging circuit, so for example, here's the FET sim where you kind of can switch it to charging and discharging. When we discharge and the charge flows through this light bulb, the voltage across the light bulb starts off at wherever it was, let's say whatever, 6 volts, decreases really quickly, but then, tapers off. So as it gets less and less charge, there's less and less electric field. There's less and less electrons on the negative plate that are repelling each other. So they get a little calmer. They don't push away as fast or as quickly. All that stuff. So it's an exponential decay, which is very exciting because from math class, you know how fun exponential decay functions are. The voltage will decrease exponentially with time. Because of our fun equations like V equals IR, and really in the data booklet they write this one like this, but the charge on a capacitor is equal to voltage times capacitance. All of these things, because the voltage decreases exponentially, so does the current flowing in your circuit, so does the charge on the capacitor. They all show exponential decay. So we use an exponential decay equation for all of these. But bam, here they are all at once. All right, all the same format. So exponential decay looks like this, yeah? Something out front times e to some negative coefficient. So here's what all the equations are. They're in your data booklet just like this. So here's what all that stuff kind of means. Let's use the first one for an example. The first variable is the function of time. So this is, Q as a function of t. This is how the charge on the capacitor changes with time. It depends on the initial charge stored in the capacitor. So we could say this is like the charge at time t equals 0. That's usually why we use a 0 subscript for this kind of thing. So we're doing Q sub 0 times E, the math E, raised to negative t over tau. Fun, Greek letter tau. All right, so t is time, the current moment in time. When we started, time t equals 0. Now t equals however long. And we divide by something called the time constant, which we'll define in a second. All right, and, we have the same equations for current and voltage because they're all just exponential decay. So your current decreases exponentially with time, same kind of decay curve. It just scales down your initial current that flows as soon as you start the discharging circuit. And your initial voltage also decreases exponentially. So we'll review a little how to use these exponential equations, but that's pretty much it. It's exponential decay. What's this tau thing though? Let's do that. Tau basically says, this says something. If you know a little bit about exponential decay, the size of the number, if I have like 2e to the negative 6, well, that tells me something about how quickly, more or less, the rate of decay. So how do we figure that out? What does it depend on? In this RC circuit, well, it depends on R and C. All right, it's just kind of defines the rate of our discharge or charging, although the IB won't have us do the charging equation. So it affects how quickly things are charging or discharging though. So like here's an example of a circuit. So again, if I had this switch up here, I would be in my charging cycle. So if this is gone, I'm charging now, current's going to flow out of the battery over here, and charge is going to build up over time on one plate of the capacitor, leaving the other plate negative. So really think of it, the battery's pulling electrons from this plate, pulling them around and cramming or sorry, I said that backwards. It's pulling because the battery is because current's backwards. So the battery is really pulling electrons from the top plate, storing them on the bottom plate. So the top plate ends up with a positive charge, the bottom plate ends up with a negative charge. And the battery can do this so much based on its voltage until it becomes totally charged and the field here is strong enough to essentially stop the battery from flowing any more current. So the charging looks like this with our voltage over time across the capacitor. Starts at 0 volts. As we add more and more charges to one side, the voltage approaches the voltage of the battery. So if there's a 6-volt battery, eventually we'll get 6 volts of voltage across the capacitor here. Now, if I switch this switch over to the discharging cycle, which looks like this, well, I will see all of that. What did I say? I have a plus plate here. Now with this, all these electrons, the battery's not, pushing anymore, so to speak, and the electrons are free to flow, so the electrons are going to flow around. So essentially current's going to flow this way off of my capacitor to equalize the charge on both plates back out. So all that current will flow, the charge will flow, balance itself back out through the resistor. All right. Well, the rate of charging depends on the size of the capacitor and the size of the resistor. That's really what it is. And so this rate depends on R and C, and it turns out it's real easy. You just multiply them together. So you multiply the resistance of your circuit times the capacitance of your circuit. And that gives you the time constant. Convince yourself that an ohm times a farad is a second. All right, that's it. So that's how you figure out the time constant, which goes in the equation for discharging. That tells you how fast the discharging is happening. All right. Charging looks like this. So again, here's the idea. You start with no charge in the capacitor, so no voltage. Eventually you increase. This stands for voltage of the source, voltage of the battery. This would be a asymptote officially. You have an exponential charging thing. So you might see exponential charging like this. You might have to sketch what's going on with the charging curve. You'll investigate it hands-on, but you won't do the equation for charging. Honestly, I don't know why they don't give it to you. It's not that much different or harder, but there you go. They'll only have you math on a discharging circuit. So you want to understand this is what happens when you charge up a capacitor. This is what the voltage across it looks like with time. It's an exponential increasing, It's like a 1 minus e to the negative something thing. And here's just a fun graph with some of these different things. Fun fact, after 1 time constant, you're 63% charged. After 4 time constants, you're 98% charged. 5 time constants, you're close enough. Infinity time constants before you're really at the equal to the voltage source, but you very quickly get up to basically the same as the source voltage. Okay, so let's just do one, and this will pretty much be what you need for how to do these. So let's say I have a capacitor yay big, 220 microfarads, and I charge it up to 30 volts. So I connect it to like a 30 volt supply, and then I flip a switch and put it to a discharging circuit, and I discharge it through a 330 kilo ohm resistor. Part A, I want to find the time taken for the capacitor to discharge to 5.5 volts. All right, so as fun as things get, we're always doing the guess method. What am I trying to find? I'm trying to find T. T is the thing I'm trying to solve for. What else am I given? Well, 220 microfarads, that's the units for capacitance, and they're talking about the size of my capacitor. So that's C. I got 2 voltages, so I'll have to think about that. I know this is going to be R, 330 kilo ohms. All right. What about my voltages? Well, it's charged up to 30 volts, and then it's going to discharge to 5.5 volts. I'm thinking this is VO. That's my voltage at time t equals 0. And this is V. That's my voltage at time t. Yeah. So that's what I got. I got to find T. Now it's just a math problem. All right. I'm going to use my equation, my exponential discharge equation with voltage, because this is about voltage. So I need to solve for T. Of course, the fun thing to think through is how do I math when I have stuff in an E exponent. All right. Well, first we'll start getting T by itself. I'll divide both sides by V0. So I got V over V0 equals e to the negative t over tau. Okay, what do you do? What do you do when the thing you're trying to solve for is raised to the power up here on an e like this? What do you do? What do you do? Rules of exponents. Rules of exponents. I think you natural log both sides of the equation. That's the move. Yeah, that's how you do this. All right, so natural log both sides, because the natural log of e to the x is just x. Natural log of e to the anything is that anything. Yeah, that's why we're doing it. Now, not too hard. I'm just going to hit the natural log button in my calculator. I'm going to multiply both sides by a negative time constant to fully do this before I plug in any numbers. V over VO. All right, so I'm just going to multiply negative time constant times the natural log of V over VO. I know V, I know VO. I just got to find the time constant. I'm going to go to that other handy data booklet equation. Time constant is equal to R times C. Not too bad. R is 330 kilo ohms, so 330 kilo means times 10 to the 3 ohms. And I multiply that by capacitance, which is 220 microfarads, 220 micro 10 to the minus 6, of course. Front of my data booklet will help me out if I forget that. Punched it in my calculator, use the E button. I get the time constant. It's 72.6 ohm farads, aka seconds. There's my time constant. I got all the numbers I need now. Let's just punch them in. So T is going to be equal to 72.6 seconds times the natural log of, what we got? V is 5.5 volts divided by 30 volts. Yep, and punch that in your calculator. Natural log, parentheses, divide. You should get 123.16 seconds. And so our final answer, we will say, because sig figs, I got 2 as my lowest number. 2 sig figs. We're going to do, the time it takes is 120 seconds. There you go. Exponents. Okay. 120 seconds to discharge. That's how you do these discharging equations. Not too bad. Let's try B real quick. So B is about charge moved from a capacitor in this time. So think about that. You try that. Go ahead. Give it a shot. Think about what other data booklet equation you might be able to use for the charge on a capacitor and what we mean by charge moved. So try. Okay. Here's the equation you want to use. You want to use the equation with the charge in it, with the Q in it, the Q and the C. So you're going to use the QVC equation. In other words, in the data booklet, C equals Q over V. All right, the capacitance of a capacitor can be defined by the ratio of the charge it stores divided by the voltage across it when it's storing that charge. In other words, if I want to find how much charge is on a capacitor, I multiply the voltage across the plates times the capacitance of the capacitor. That will tell me how much charge. All right, so what do we mean by the charge moved? Well, I had different voltages, right? I started with 30 volts across the capacitor, and then I ended up with 5.5 volts across the capacitor. So it had a bunch of charge on it. When it had a high voltage, it had less charge on it. When it had a smaller voltage, that charge moved through the circuit and created some heat in the resistor and then went back to the other plate. So how much? Well, what I didn't want to do is find how much charge is on it in the beginning and how much charge is on it at the end. Yeah. So all I got to do is use this equation twice. In the beginning, it had a charge equal to the voltage across it, 30 volts, times the capacitance of the capacitor, 220 microfarads. And that gives me 6.6 times 10 to the minus 3 coulombs of charge. And then at the end, I had 5.5 volts across my capacitor, same capacitance. Multiply. Remember, that's 10 to the minus 6. So that's really 220 times 10 to the minus 6. And I get 1.21 times 10 to the minus 3. So I started with this much charge in the plate. I ended with this much charge in the plate. The amount that got transferred must be the difference. Yeah, it's like how much left the plate. How much left the one plate and went back to the other plate. So all I do is subtract them. I'm going to do Q final minus Q initial. To subtract those two numbers, you get 5.39 times 10 to the minus 3. So we're going to sig fig round that again and call it 5.4, I don't know, how about millicoulombs? Sounds good to me. All right, so lots of fun capacitance equations, exponential math, that kind of thing, but that's how you handle them. All right, so you'll be doing that with some lab stuff, you'll be doing that with some problems and beyond. So have fun.